Okay, here we're just going to look at another projectile example. This one is going to be different in that it's going to have a rock that is thrown off from a height, so there's going to be a vertical displacement, so off the edge of a cliff. And that rock is also going to have an initial velocity that has both a horizontal and vertical component. And so it's sort of a combination of the last two problems where we dealt with the an initial velocity at an angle and something falling. A rock is thrown off a cliff. It's 10 meters tall. So here's the cliff. The rock is shot off the edge of the cliff with 10 meters per second, 25 degrees above the horizontal. Determine the maximum height of the rock from the bottom of the cliff, so it does specify from there. Determine the impact velocity of the rock. Determine the horizontal range of the rock. It says the cliff is 10 meters tall. 10 meters per second at an angle of 25 degrees above the horizontal. So the first thing is we know we're going to handle this problem separately in the horizontal and vertical directions. So let's divide that 10 meters per second into its components. 10 meters per second sine 25, because this is the opposite side. .23 meters per second, and 10 meters per second cos 25. This is the adjacent side of the triangle. 10 cos 25, 9.06 meters per second. So now we can divide up our vertical and horizontal information. The maximum height of the rock is a little bit different because all we really need to consider here is the vertical information. I'm going to do that problem first, get to the answer of it, record that answer, and then I'll go back and deal with the other two issues, the impact velocity and the horizontal range. In the vertical direction, we have an acceleration of negative 9.8 meters per second squared, free fall. We have an initial velocity of 4.23 meters per second. If we're going to go to the maximum height, what that means then, if we imagine this rock is going to come up and come back down, at that maximum height it has to stop so that it can turn around, so we have a V2 of 0. And what I'm really interested in here for my maximum height is the displacement when it's at that spot where it's stopped. Sorry about that. Where was I here? Delta D. I don't know what happened there, but that's okay. I'll just rewrite that part. So 2a delta D is equal to V2 squared minus V1 squared. 2 times negative 9.8. V2 squared is 0 minus 4.23 meters per second squared. So negative 19.6 meters per second squared, delta D is equal to 4.23 squared. Which turns out to be 17.89 meters squared per second squared. And if I divide both sides by negative 19.6, careful here, again, we talked about this in the earlier unit, this negative is outside of the brackets, and so when we do that square, we don't square it away. So we can see that the rock is going to travel an additional 0.913, or just a little bit less than a meter, further than its initial height. Now let's be a little bit careful here. It says the maximum height of the rock from the bottom of the cliff. So if the cliff is 10 meters tall, and we go up an additional 0.913 meters, what that means then is that my height at the max is equal to 10.913 meters. So that's that. And I'm going to be really careful here. Maximum height, impact velocity, and horizontal range. I don't want to mix those things up. Because if I imagine this motion, I'm going to redraw it just to make the point. So here's the rock, here's the cliff. So it comes up and it's going to go back down. The max height occurs right here. So this projectile has gone up and stopped at this location. And those are sort of my parameters for what I want to calculate. To get the horizontal range or the impact velocity, I'm going all the way down to this point right here when the rock is hitting the ground at the bottom of the cliff. See, max height goes to here and those two both go down to here. So these two are going to use the same set of given information, but it's not necessarily going to be the same as the given information we used for the maximum height. So it's a good thing to separate those two things out and think of them as two separate problems because they're going to totally different points, so we're going to get different amounts of information. Just making some space for me to do the second part of this here. Okay. So if we go back to our original problem, now we're going to deal with the horizontal motion as well. So we've got the vertical, and again the acceleration is negative 9.8. The initial velocity is v1, 4.23. The difference is we can no longer say that v2 is equal to 0 because we're not going to the top of that motion. The other thing that's different is that now, because we're going down to the bottom of the cliff, we're dropping that 10 meters. We do know one more piece of information about the vertical, specifically that the displacement of this rock in the vertical direction is going to be 10 meters. With that, we can do two things. We can find the horizontal range by recognizing that it is uniform motion, acceleration equals 0 in the horizontal direction, initial velocity of 9.06 meters per second. And so if we can get time, we can bring that over. And the secondary thing we can do is get v2. And with those two things, we can find the impact velocity in the horizontal range. Let's do horizontal range first. No good reason. Delta D equals V1T plus 1/2 AT squared. Negative 10 equals 4.23 T plus 1/2, my acceleration is negative 9.8 meters per second squared, T squared. And I'm just going to simplify this a little bit, not even all that much. Negative 10 meters equals 4.23 meters per second T. I'll just put that in brackets just so that's clearly separate from the variable. Minus 4.9 meters per second squared T squared. Now let's just be a little careful here. Let's just look at this. We've got a t and we've got a t squared and we've got a constant term. That means this is a quadratic. And we don't have any zeros to work with and we've got lots of decimal places. So the easiest way to solve this quadratic is going to be to use the quadratic formula. Before I can use that though, I have to get everything on one side. So let's move everybody over to the left. So I got 4.9 meters per second squared t squared minus 4.23 meters per second t minus 10 meters. and all of that is equal to 0. Now, if you have a calculator, chances are there's a way to use it to solve the quadratic formula. Depending on your type of calculator, you're going to have to press different buttons to make that work. I suggest you go onto a different YouTube video and look at how to solve the quadratic formula directly. But for the purposes of this video, we'll do it the old-fashioned way. So negative b, remember this is a, this is b, this is c. So negative b means negative 4.23 meters per second squared, plus or minus the square root, negative 4.23 meters per second squared. Oh, that's not meters per second squared, that's just meters per second. And that is squared there. Minus 4 times a, which is 4.9 meters per second squared, times a negative 10 meters, all divided by 2 times 4.9 meters per second squared. So it's a little annoying, but here we go. 4.23 meters per second plus or minus. I'm just going to save a little bit of time actually and fire through all of this all at once on my calculator. So this is all equal to 14.6. And it would have been meters squared per second squared until I square rooted it, and then it's meters per second. Divided by 9.8 meters per second squared. So I got negative 10.4 divided by 9.8. As that'll turn out to be my negative root. Or 18.86. And that'll be my positive root. And I'm calculating the negative root here, but I'm sure if you realize or you think we're not interested in a negative time, you could have stopped and not calculated that. But I'm just doing it all to be complete. So that one's negative. So this is the root we're interested in. Just for whatever it's worth. If we imagine this rock coming off the cliff and landing, remember our numerical model doesn't know that we shouldn't go back in time, and so it creates a false root down here. That's why this false root is created. One way or the other, it doesn't matter. 1.92 seconds is the time that we want. So what that means then is I have a time of 1.92 seconds. Whatever time it's in the air, that's the time it's in the air. Delta D, now I'm working in the horizontal direction. Using the big formula, even though my acceleration is 0, I've addressed that already. And I've got a 0 for my acceleration here, so this whole term is ignorable. Let's not get these things confused. In fact, I can just erase that because I'm focused here. So I'm going at 9.0 meters per second for almost 2 seconds, and that means that I'm going to travel a distance of 17.4 meters. And that's my horizontal range. So this is horizontal. So that's how I found the horizontal range. Now we'll go back one more time, and we're going to take all this information and we're going to find, so we got u, we got u, we're just missing our impact velocity, which actually is going to be a little bit easier than horizontal range in this question, since we won't end up with a quadratic. So V2 is question mark, and I'm going to go way over so I have some space to write and use this equation. In the vertical direction, I have 2a d delta d, 2a delta d is equal to v2 squared minus v1 squared. My v1, my 2 times negative 9.8 meters per second squared. Remembering that this object is falling a distance of 10 meters as it goes from the top of the cliff to the bottom of the cliff. So that's our displacement. V2 is what we're looking for. And V1 all the way over here at 4.23 meters per second. This one right here. So this is going to work out to 196 meters squared per second squared. And that's all of those terms, and the two negatives become positive. V2 squared and 4.23 squared. Remember that minus is outside of the brackets, as I've said a few times now, so 17.89 meters squared per second squared, but the minus remains. So when he comes over to the other side, it becomes a plus. So I got 213.89 meters squared per second squared. It's equal to V2 squared. And now I'm going to square root. This square root's one of those tricky ones where we have to remember that we're introducing the plus and the minus root when we square root. 14.6 meters per second, and that's V2. Keeping in mind that this object is falling, then I know that I need my negative root here. So V2 in the vertical direction is negative 14.6 meters per second. Now, all the way back over here to this, what we started with. Started at 9.0 meters per second, 9.06 meters per second in the horizontal direction. And remember that the acceleration in the horizontal direction is 0. So that means if that's the velocity I started with, the velocity I finished with in the horizontal direction is the same. So all the way over to what I'm talking about now, if I'm going 9.06 meters per second because it's constant horizontally, and negative 14.6 meters per second down as it's accelerated to, I can get the new impact velocity, or the impact velocity. V squared is going to be equal, or sorry, I'll just put the square root in right over here. Square root of 9.06 meters per second squared plus 14.6. I did the negative, but it doesn't matter because I'm squaring it. Trying to remember to be thorough with the units here. Alright. And I'm just going to fire right through that. That will be 17.2 meters per second. Careful here. If this is my angle, this is my opposite, and this is my adjacent. So remember, tan theta is opposite over adjacent, which means I have 14.6 divided by 9.06. And because I'm going to interpret the sign later, I don't want to put signs into this equation. So I'll inverse tan that ratio. And I get 58.2 degrees. So my impact velocity is 58.2 degrees below the horizontal. Another way of specifying that direction, for whatever it's worth, is that I could say that it's going x, negative 58.2 degrees y. That system's a little bit more similar to our heading system that we learned when we were doing displacement in two dimensions. So here we say that we went x first, and then the negative 58.2 degrees y implies that it's down. So that's a big projectile question. You can see that these things get quite involved, but I think if you're just focusing on getting through it, it could be a little bit shorter, just trying to show everything involved. I'm going to do one more of these before I stop, and then, well, I'm going to stop here and create another video with one more of these for one more projectile example.